In 2020, population in the world is currently growing at a rate of around 1.05% per year, reaching at a total of 7.8 billion as of March 2020. However, the global population is still increasing and is projected to reach about 10 billion in 2050 and more than 11 billion in 2100. As a result, global food demand is also increasing rapidly. In order to feed 10 billion people sustainably by 2050, we will have to close the 56% food gap between crop calories produced in 2010 and those needed in 2050 under usual business growth. At the same time, we urgently need to cut greenhouse gases emission from agricultural production and stop conversion of remaining forests to agricultural land. Urea, which is also known as carbamide, is one of the solutions to solve the ongoing challenges. It is a colorless crystalline substance that is often used as a nitrogen-based fertilizers. In fact, it covers up to 57% of the world total consumption. Fertilizers are chemical substances supplied to the crops to increase their productivity. To simplify, fertilizers are actually food for the plants. It helps the ground to provide the essential compounds needed for the plants to grow and thrive, thus helping the farmers to grow healthy foods for the world population. With the various advantages of urea, there comes various processes in synthesizing the urea, namely Stamicarbon process, ACES process, and Stamprogati process. Among them, the most common one used in the industry is the Stamicarbon process.
The Stamicarbon process is a urea production process that utilizes CO2 as a stripping agent. The process starts with an exothermic reaction between ammonia and carbon dioxide to form ammonium carbamate. Then, in another reactor, carbamate is dehydrated into urea and water. This is an endothermic reaction. The optimum process condition for the dehydration of carbamate is around 145 bars and 180 degrees Celsius, with a nitrogen to carbon ratio of 3. The dehydration of ammonium carbamate is an equilibrium reaction. Thus, the reaction mixture from the reactor has to be subjected to high pressure stripping. The stripping agent used is carbon dioxide, as it can remove non-reacted ammonia and carbon dioxide. In all CO2 stripping processes, ammonia and carbon dioxide are fed directly to the synthesis section. The gas from the stripper is then sent to a pool condenser. There, the gas is condensed into a pool of liquid fresh ammonia and overhead vapors. The pool condenser is a horizontal vessel with a U-tube bundle submerged in it. Within the tubes of the heat exchanger, low-pressure steam is generated. This equipment combines the functions of a conventional falling film type carbamate condenser and a urea reactor. Thus, the reactor volume can be decreased by about 30 to 40% compared to conventional processes.
As you can see, exhaust gases from the top of the pool condenser are then scrubbed in high and low pressure scrubbers. This is to minimize ammonia emissions. A separate high-pressure ammonia recycling stage is not needed in this process because the concentrations of ammonia and carbon dioxide are low in the stripped urea solution. The ammonia and carbon dioxide present in the discharged urea solution from the stripper are recovered in the low-pressure recirculation stage. The urea solution that leaves the recirculation section is concentrated further in the evaporation section from 74 to 98% by weight. Evaporation is done in a vacuum to minimize burette formation. Now looking at the process flow diagram, all the condensate from the evaporation section is then treated in desorption and hydrolysis sections. Ammonia and carbon dioxide are stripped off in a stack to desorber column, and small amounts of urea and dissociated in the hydrolysis column. The treated condensate can be used as make-up water for cooling water cycles because of its high purity. It could even be used as boiler feed water after polishing. Thus, the Stamicarbon urea process has no waste water effluent.